Yesterday I left you guys after showing you an equation that we could use to solve this particular problem. I realized that a lot of you didn't completely understand where I got the pieces of information from that I plugged into that equation. So I wanted to show you guys, if we were to solve this problem from the start using that equation, how we would have to get those numbers that we plugged in. When we solved this problem yesterday, we took a roundabout path to get to using that equation. And in that roundabout path, we calculated the numbers that we needed for that particular equation. But I want to show you guys how solving this would look if you didn't have that roundabout path and you had that equation and you had to generate the numbers needed to use that. So the equation that I left you with was pH is equal to the pKa plus the log of the concentration of A minus over HA. A minus, just the negative ion produced from the acid. A stands for anion. Anion is just a negative ion. So we're talking about the acetate ion. HA, talking about the acid. So if I can find, at the point of neutralization, the concentration of A minus and the concentration of HA, I can plug those in and find the pH. At the point of complete neutralization, all of the base has reacted with the acid, so there's no acid or base present. There's simply salt and water. At this point in the reaction, we have the acetate ion, CH3COO minus, reacting with water, producing CH3COOH and OH minus. So the concentration of the negative ion present will be the concentration that we have here, less what reacts to form this. The concentration of the acid, well, we don't have any acid from what we initially started with because that was all neutralized, but we do have acid being produced from this reaction with the salt. So if I could determine the concentrations of this and this, I could plug them in here and here. Now we do have to look at an ice table to decide what these concentrations are. We determined yesterday that the concentration of the acetate ion was 0.0500 molar. Talk about how the water doesn't matter. And initially these were 0 molar and 0 molar. Then as the acetate ion started to react with the water, it decreased by some value. This increased and this increased. At equilibrium, we'd have 0.0500 molar minus X. Here we'd have X. Here we'd have X. So this is the piece that I would need to plug into the equation. This is the piece that I need to plug into the equation. What we looked at yesterday, well, we were told the Ka of the acetic acid. Ka of acetic acid is 1.8 times 10 to the minus fifth. And from that, we determined the Kb for the acetate ion, which is its conjugate base. The acid and its conjugate base, the Ka and Kb, are related. Ka times Kb is 1 times 10 to the minus 14th. We calculated Kb to be 5.5556 times 10 to the minus 10th. Because that is very small, we made the assumption that this was like subtracting 0. So at equilibrium, the concentration of the acetate is 0.0500 molar. And we use that to find the hydroxide ion concentration. We said the hydroxide ion concentration is equal to the square root, the concentration of the base times Kb. We plugged in the concentration of the base, we plugged in Kb, we found the hydroxide ion concentration. The hydroxide ion concentration is the same as the concentration of CH3COOH. So from solving this, we can find this X and this one, which is the one we need. And we determined that to be 0.046 times 10 to the negative 6 molar. Thank you. So now we have the two pieces that we need to plug into this equation. We can plug in here the 0.0500 molar, and we can plug in here the 5.27046 times 10 to the minus 6. Now you can see that though this equation does eliminate a lot of the work that we did yesterday, so I just did that in a matter of minutes as opposed to yesterday taking the majority of the hour, there is still some work you have to do to use this equation at a point of complete neutralization. Hopefully that helps some of you kind of clarify where those numbers came from and how you use this equation to solve. Questions? Okay. A few more problems that we're going to look at today, and then you guys are going to get some work time at the end of the hour. Yesterday we determined that in order to completely neutralize this particular solution, it would take how much base? Look back in your notes. How much base did we decide? It would. Yesterday we calculated how many milliliters of sodium hydroxide would be required for complete neutralization. How many milliliters did we calculate? 0.0500 liters, which is 50 milliliters. So we know to completely neutralize this acid solution, we need 50 milliliters of base. In this particular problem, we're only adding 10, which makes this a partial neutralization. This means that we're going to have excess acid after we've added the base. Let's talk about, because we have a strong base and a weak acid, how we will use this equation to solve this particular problem. If we want to use this equation, we need to know the Ka for the acid, which is 1.8 times 10 to the minus 5th. So we have that to plug in here. We need to know the concentration of the negative ion and the concentration of the acid. Well, we know we're going to have some acid remaining. We know we'll have some salt form, some negative ion form. Let's take a look at that. In order to figure that out, we need to know how many moles of acid we have. We need to compare that to how many moles of base we're adding. So 0.100 molar times 0.0500 liters, 0.00500 moles of acid. Here we have 0.100 molar times 0.0100 liters is 0.00100 moles. Oops. Of base. Now, according to the balanced equation, the acid and the base react in a 1-to-1 ratio. Because they react in a 1-to-1 ratio, if 0.00100 moles of base reacts, how much acid will react? The same amount, 0.00100 moles of acid will be reacted. So how much acid will be unreacted or unneutralized then? 0.00400 moles. So we have 0.00500 moles of acid. We know that if 0.00100 moles of base reacts, an equal amount of acid will react because it's a 1-to-1 ratio. So minus 0.00100 moles that will react. This will be 0.00400 moles of acid. that is not neutralized. And this is the value that we are going to plug in here. Now, I know that some of you might be thinking, and those of you who aren't thinking this yet, follow this. When that amount of acid reacts, won't some of the negative ion be produced? Some salt will be produced when the acid and base react. And when the negative ion in that salt reacts with water, won't acid be produced as well? So we not only have the unreacted acid, but we also have some acid produced from the salt reacting with water. However, remember that this has a very, very, very small Kb. So that means that very, very little of this will form. And if very little of this forms, will it be significant relative to the acid that we just have remaining in the solution? No. So we get to exclude that piece and plug this in, knowing that this is the significant contributor of the acid that's in the solution. Okay, so now we just have to figure out the negative ion piece. Well, we just said that 0.00100 moles of this reacts. If the acid forms a salt in a 1-to-1 ratio, how much of the negative ion will form? 0.00100 moles of the negative ion will form. That will allow us to plug that number in there. Again, some of you might be thinking, well, doesn't some of that get used up then when it reacts with water? But the amount is not significant compared to that amount, so we'll plug in this here, we'll plug in this here. So to calculate the pH, yes? I'm about to get to that. The question was, don't the moles that we're plugging in have to be in molarity? If you looked up this equation in a textbook, you would see concentration written as part of the equation. But if we were to hang on, let me get this. If we were to change both of these into concentration, we would have to divide both of these by the volume that they're in, right? And they're both now in what volume? So we've added 10 milliliters to 60. So we would essentially be taking 0.00100 moles and dividing it by 0.0600 liters to get it into concentration. To get concentration on the bottom here, we'd be taking 0.00400 moles and dividing it by 0.0600 liters. If we take 0.06 divided by 0.06, what happens to the 0.06? It just cancels out. So because of the fact that we're dividing these two values, we can use mole values as opposed to molarity, and it's going to give us the same answer in the end. Technically, yes, they should be in concentrations, but let's save ourselves a little bit of work. Just plug in moles. So we just need to plug in 0.001 divided by 0.004. So I'll let you guys calculate this. And again, I encourage you guys to make sure you're getting these numbers on your calculator. I'm grading test 1, and I cannot tell you how many students have the right equation, their work looks great, and their answer is something crazy. Now, yeah, well, yes, technically, because that's how much NaOH reacted, so that's how much acid would react as well, because it's a 1-to-1. And this is where the negative ion comes from. So if 0.001 moles of this reacted, we get 0.001 moles of salt, which would be then 0.001 moles of the acetate ion. But yes, it should always be equal to the amount of base that reacted if it's a 1-to-1 ratio like we have here. So negative log of 1.8 times 10 to the minus fifth plus the log of 0.00100 divided by 0.00400. What do we get? 4.143 with significant figures. Okay, let's do another one. Another partial neutralization, this time at the halfway point. The halfway point is 25 milliliters. Remember, we said that it would take 50.0 milliliters of the sodium hydroxide to completely neutralize the solution. So halfway would be if we have added 25. Again, we know we're going to have excess acid. We're not adding enough base to completely neutralize the acid. So this calculation is going to be really similar to the one we just did. We have a weak acid and a strong base, so we'll use pH is equal to pKa plus the log of A minus over HA. To find the pH, calculate how many moles of acid and how many moles of base. We'll use this to figure out how much of the unreacted acid we have remaining and how much of the negative ion was formed. Again, we can neglect that kind of side reaction, if you will, because it won't be significant compared to the acid remaining and the negative ion formed from the reaction happening at a partial point. So 0.100 molar times 0.0500 liters, 0.00500 moles. .100 molar times 0.0250 liters, 0.00250 moles. If 0.0025 moles of base react, because it's a 1-to-1 ratio, how much acid will react? .0025. So if that much acid reacts and we start with 0.005, how much acid will be remaining? Okay, so we'll have 0.0025 moles of CH3COOH that is not neutralized. So here we have the piece of information that we need to plug in there. Now we just need to figure out the negative ion concentration. Well, we said that 0.00250 moles of acid react, and this is a 1-to-1 ratio. So how many moles of the acetate ion will form? So 0.00250 moles of the acetate ion will form. So that will allow us to plug this in here. 0.0025 over 0.0025 is what? 1. Those of you who have studied logs, the log of 1 is 0. If this is 0, then what does pH equal? pH is going to be equal to what, John? pKa. And this will be true at any halfway point for a weak acid and a strong base. For weak acid and a strong base at any halfway point. So if on a test, I say, here's a whole bunch of information about an acid, here's a whole bunch of information about a base, it's a weak acid and a strong base, none of the other numbers matter in that problem except for the Ka, and this should be the easiest problem that you do on a test. Yes, except for the ones where the pH is 7. So if we calculate pH, pH is going to be equal to the negative log of the Ka, which is 1.8 times 10 to the minus fifth. What is the pH? 4.745. Perfect. All right, the last problem that we'll look at today. We have a weak acid and a strong base, and we have excess added. So still the same problem that we were looking at in the last couple, but now we have extra base added. We only needed 50 milliliters, and at this point we've added 75. If we have extra base, what kind of pH should we see? Something greater than 7. So we would anticipate seeing a pH greater than 7. Let's first start by figuring out how much extra base we have. The pH is going to be determined by the excess base. At this point, we're essentially just going to have a solution. The acid's been completely neutralized by the base, and we have extra, because it's a strong base, extra hydroxide ions. So let's figure out how many extra hydroxide ions we have. Oh, didn't need that extra zero. 0.00750 moles. If I have 0.005 moles of acid, 0.0075 moles of base, how much extra extra base do I have if they react in a 1-to-1 ratio? I have 0.00250 moles of excess sodium hydroxide. Well, I could calculate the hydroxide. I can calculate the concentration of the base. And because this is a strong base that we now have in solution, we can calculate the hydroxide ion concentration because it should be equal to the concentration of the base. And we could find pH from there. So let's calculate the concentration of sodium hydroxide. This will be equal to 0.00250 moles of sodium hydroxide divided by at this point, what's the volume? 125, so divided by 0.125 liters. This is 0.0200 molar. If that's the concentration of the base that's extra in the solution, what's the concentration of the hydroxide ion in the solution? Is this a strong base or a weak base? Strong base. So Emily, you said that the concentration of hydroxide ion should be the same, 0.0200 molar. I'm guessing you did for a weak base. So strong base, so the hydroxide ion concentration is the same. We can find the pH in one of two ways. We can calculate pOH, which is the negative log of the hydroxide ion concentration, and from that find pH. Or we could calculate the hydronium ion concentration, and from that calculate pH. And either way we'll come up with the same answer. What did you get? 12.301. Mackenzie, will you shut the door? Again, guys, I just want to show you how the titration curve would be generated based on the calculations that we just did. Titration curves all look generally the same. If we are titrating a weak acid with a strong base, we're still going to get the same curve, but we're going to see different values at different points. So we talked about the equivalence point for the last problem being at 50.0 milliliters. And at that point, what was the pH? Because it was a weak acid with a strong base, it was slightly above 7. And what was that? The equivalence point is the point of complete neutralization. At the point of complete neutralization, what do we determine the pH to be? You'd all have it in your notebooks. You'd only flip back one page. 8.722. Halfway point is 25 milliliters added. At that point, what was the pH? The halfway point. We just did that today. 4.745. We also did at 10 milliliters. Okay. At that point, what was the pH? 4.143. And we calculated at 75 milliliters. At that point, what was the pH? 12.301. Do you guys see how, regardless of whether we have a weak acid and a strong base or a strong acid, strong base, we get these numbers, but the equivalence points, halfway points are going to depend on, well, what kind of solutions we have, and then the pHs will also be dependent on that. But regardless, we get the same kind of curve. We have very small changes at the start, and we have a huge change once we get near the equivalence point, and then we'll have very small changes following. We could do this experiment in the lab, and we would generate a curve like this, and we could measure the pH at different points, and we should see these same things that we just calculated here. That is all I have for you guys.